Hello IAB, this is David Wingate from BYU, and I will be giving you an update on our project, Probabilistic Programming for Perceptually Driven Autonomous Agents. The goal of this project is to use probabilistic programming to enable a new level of programming high-level behaviors into UAVs and to connect low-level perception with high-level reasoning. Our goal is to go from pixels and raw inputs to three-dimensional representations of the world like point clouds that can be turned into maps. And because of the inherent uncertainty in all of that, we use a Bayesian framework. We're particularly interested in modeling other agents and their beliefs, desires, and intents, so-called theory of mind. What are other agents up to? What do they want to do? We include a comprehensive Bayesian model that includes all of these elements. We talked about some of them in our last report. We use RRTs as a model of the planning, not of our planning, but of the planning of other agents. So this is a distribution over how we think they might behave. Similarly, we use things called isovists to accurately model the field of view of what we think other agents can see. Tie it together into a Bayesian framework to ask, what are they trying to do? So we have some new results that we'd like to share on our theory of mind work. The short story is better models or better detection rates. Last time we talked about some convergence results that showed that our probabilistic programming framework could successfully infer a wide variety of things. Today I'll tell you a little bit more about the intruders. We start with the naive intruder that just goes from point to point, upper left-hand corner to the lower right-hand corner. Doesn't reason about the fact he's being chased by a UAV. His code looks something like this. A naive agent, or UAV, who's searching for the intruder might use a simple grid search, like this. If you pit the simple intruder against the simple UAV, you get a detection rate of about 63%. Now, of course, a real intruder would do much better than a naive plan. He would know that he was being chased by a UAV, so he might do a planning algorithm that tends to favor small areas in the map, or little alleyways, places with low visibility. We can represent that in our probabilistic programming framework as a small optimization problem, where the smart intruder considers multiple paths, calculates expected visibility for each of them, and then picks the one that it thinks will be the least likely to result in detection. It's a little bit complicated, but if the intruder does this, he is indeed able to reduce his detection rate from 63% to 52%, a win for the intruder. Of course, a smart UAV might know that that's what the intruder was trying to do and might explicitly model that. Here's the probabilistic programming code for a smart UAV against a naive agent, a naive intruder. It uses as a subcomponent of its model an explicit model of how it thinks the intruder is behaving. Inference in this model is much more complicated, but you can do it. And as we see in this result chart, the smart agent versus the naive intruder is able to recover a high detection rate of 74.4%. Of course, I mentioned that it's computationally intensive. So the question is, what about the smart UAV versus the smart intruder? This is the result in the lower right-hand corner. Unfortunately, we don't yet have that. It turns out that it's computationally intensive enough to run this nested reasoning that we haven't been able to do it. So I'd also like to share with you a few results on going from in the first part of our model, going from pixels to point clouds. As I said, our ultimate goal is to start with raw pixels and then build up to these high-level representations such as map that support theory of mind. We've recently been doing some work using point cloud-based visual odometry and implementing that using our probabilistic programming framework. Actually, we use TensorFlow, which is a machine learning framework, to help us. We're able to recover reasonably high-quality point clouds from raw pixels just doing visual odometry and recovering the point clouds as a byproduct of the optimization of the camera positions. So our goal is to fuse this sort of odometry and point cloud-based mapping with our high-level theory of mind. Thanks.